because I know we have people with busy events and stuff this weekend too. So FRQs 1 and 2 are it. Okay. So voltaic cell. When I say voltaic, what does that also mean? What does that also mean? Thermodynamically favored, so spontaneous. Delta G is what sign? Negative. E cell is positive. K is way greater than 1, right? Usually very spontaneous or very thermodynamically favorable for reduction. So I've gotten up one word into the sentence, and we know all that junk about this. Great. They are using this to replace silver by aluminum. What is that reaction? Silver by aluminum. Yeah, but tell me, like, which is the ion, which is the solid? I want you to understand this phrase. So the replacement of silver by aluminum being silver is the ion, because the ion is usually in a compound, like an ionic compound. So silver, you're telling me is the ion, by aluminum being the aluminum solid. What would that yield? And can you guys do these two half reactions in your head?
Yeah.
So silver is going to go to what? Because it can't go up, right? We're going to go to silver solid. And is that being oxidized or reduced? So it's going from ion to solid, so 1 to 0. That is reduced. By how many electrons? 1. Okay, so keep that in your head. Aluminum has to go to what? Because it's its highest oxidation state, its highest charge is 3, and that's the only point for aluminum. Okay, so that looks as if it's being oxidized, so we're in good shape. You should double check if one's oxidized, one is reduced. By how many electrons? 3 electrons. So this one's 3 electrons, and this one's 1 electron. What are multipliers?
3.
So just 3 on the silver will do? So do you see we can sometimes, for these easy ones with just metals, you can figure out the half reactions kind of all at once. Is that okay? Good with that? Okay. So what effect do each of these changes have on the electromotive force? What am I asking? What is this? The voltage, right? EMF, electromotive force is E cell. So you can now tell me quantitatively and qualitatively how E cell is affected by using Le Chatelier's principle. We saw in the video yesterday. Sorry, it was long, but you had to watch it. So in terms of adding water to the anode compartment, we need to figure out which is the anode compartment first. What is in the anode compartment? The one being oxidized, right? So the one being oxidized is aluminum and aluminum ion, right? They're all in the same compartment together. So I'm just going to put anode here to say this guy is in the in the anode compartment, and then the cathode would have to be silver and silver ion, right? So this is a little bit further, but we know that's the cathode compartment. All right, so if I add water, what does that mean I'm doing to the anode ion? Okay, so you're thinking about Le Chat, thinking about the Nernst equation. What's in the Nernst equation? Q. Well, that means concentration is of importance. So concentration of products over concentration of reactants. So if I dilute silver ion concentration because I'm adding water, what am I technically doing to this reaction? But why am I shifting right? Right, so you guys write down an explanation as we're going here. But decreasing the concentration of aluminum decreases a product concentration, and that's going to cause us to shift right. If we shift right, forward direction, what does that do to E cell? Increase or decrease E cell? Increase, because you are increasing the driving force of the forward direction. That's the best phrasing I can think about. So here's my 2 cents. Adding water to the anode dilutes the aluminum ion, which causes a shift right in the above equation, and will increase the E cell because it favors the forward direction and increases the driving force of the electrons. So the driving force of the electrons is what we're really talking about for E cell. So I'll let you guys finish writing that. Okay, so that's our Le Chat's kind of explanation. And you legit could, if I told you concentrations, you could plug this into the Nernst equation, into Q, and then your initial E cell would just be whatever the difference is at standard for those, and you could find the new E cell. So we would expect the E cell to be bigger than what this standard E cell is. Yes? This is bigger. Okay. 2, B, the size of the aluminum electrode is increased. What's your initial instinct here? Why? Okay, so remember we said size doesn't matter, right? Aluminum and silver, their actual electrodes are irrelevant. It's the about the surface area on it, and it's about the just identity. So the size of the electrode has nothing to do with the electrode potential or the potential difference. And a good term to use here is that the E cell itself is an intensive property, meaning it doesn't. Do you remember what intensive property means from honors chem? Right. It doesn't matter how much you have of it. It's the identity. It's the property is about the identity, not how much you have. An extensive property is something like volume and mass. It does matter how much you have of it because it changes the actual value. Like if you have more of it, the volume is bigger. If you have more of it, the mass is bigger. So an intensive property, I think this is under B, yeah, is what we would describe E cell as, and that would be a good way to describe why the mass doesn't matter in this case. C, a solution of silver nitrate is added to the cathode compartment, increasing the quantity of silver ion, but not changing its concentration. Instinct here. Why? Right. So if I said increasing, so this is basically saying you're just pouring more of the same molarity solution in it. The concentration is not changing, so no change in concentration of silver would cause a no shift. And if there's no shift, well, the Chatelier is the E cell itself does not change either. Thanks for jotting this down because this is your problem set. You'll finish the rest of it up after electrolytic cells next week. Hydrochloric acid is added to the silver nitrate solution. Give me some initial thoughts. Okay, I hear dissolve and I hear what? What's forming? Silver chloride. You guys see the silver ion and the chlorine would come together. So then if silver chloride is forming precipitate, what is that doing to our stuff we're interested in? So removing silver ions does what to its concentration? So if we reduce silver concentration, this side of the room, which way does it shift? So where's the silver? So we are shifting left. So decreasing this reactant concentration shifts left.
All 10th graders report to the auditorium at this time. Teachers, please dismiss 10th graders to the auditorium at this time.
So if it's shifting left, what happens to E cell? Okay, so we should know that whenever we're talking E cell, galvanic cells, we're talking about the forward direction. So anytime when we counter the forward direction, we should be decreasing our E cell. So it's going to decrease E cell because we're decreasing, we are showing the favorability of the reverse direction, which is not going to increase our electron flow. So we're always referencing something about the electromotive force or the drive of the electrons to be lost. In this one, there's not a big drive for the electrons to be transferred. Right, so that's all qualitative. And if you had a value, like for this one, you could literally just look up the E value of the differences between aluminum and silver, and you could predict the E cell, which is what they like to kind of go towards in the exam, but you might have to calculate it too, so that's why I want you to know the Nernst equation. Okay, I'm going to have you guys just simply set up this next cell for A, and then we'll do B, C, and D later, okay? Set the next one for A in accordance with how the reaction's written. So the replacement of nickel 2 with zinc. So what is your equation you're working with? What are the reactants? So nickel 2 plus and zinc solid good goes to. So zinc is going to be what to zinc 2 plus? Oxidized, okay. And nickel 2, nickel solid, and that's being reduced. So who's in the anode? Right, the anode is our zinc and zinc ion, and then the cathode is nickel and nickel ion. And you could, for the standard conditions, these are on at 1 molar, you would just find them on the reduction potential and subtract. Red minus, so nickel minus zinc. The other ones, what would you be employing for B, C, and D, really? But what would you do for B and C? to find the E cell. It's the title to this problem set. Nernst equation. So these concentrations you'll be plugging into where? And the Q, right? And how would Q be set up for this reaction? And I will say that there are 2 electrons lost and gained for each side of this half reaction, so there are no coefficients to include. So tell me what Q setup is for the next part. Before I turn on what's free. Okay, so zinc ion, so products. Why are we excluding this solid over nickel 2, excluding the zinc? And if they were coefficients, you'd include them, but these concentrations just get plugged in, and you plug into the Nernst equation and go. What would the N be in the Nernst equation there for this part? Why 2? Right, there's 2 moles of transferred in the half reaction with nickel and 2 with zinc, so the net changes of 2 moles of electrons. Okay, we'll finish up. We'll do some more of those, but at first, I just want to make sure you're good with the concept. Okie dokie.